Hey, thank you so much for being here so early and coming to this talk. Just a bit of a vibe check. How many of you played around with AI developing something? And how many of you tried to find bugs in code with AI, like hacks? Oh, almost everybody. That's really cool. Yeah, that's what we try also every day. It doesn't go well every day, as you might have experienced. Um, I'm Jan, the managing director of Oak Security, one of the managing directors. My background is statistics and machine learning, so that is basically AI before it became generating text. And I have a PhD in econometrics, so very data-heavy applications and particularly causal models that are my strong suit. And by accident, I run a cybersecurity company. Um, we have 52 security researchers, over 600 audits completed, and 7,000 issues discovered. At the moment, we work with partners like the Web3 Foundation, but also the Ethereum Foundation, Solana Foundation, and many other projects that you might find here. And every day, we think that our business might be disrupted by tomorrow. So, for example, last year we had this headline on Hacker News where Google found one of the first critical vulnerabilities with AI in a code base and could fix it before hackers could act. Then, in May, OpenAI's O3 model spotted a critical vulnerability in the Linux kernel, and the 0-day could be patched. And now, only 2 weeks ago, AI agents climbed the top of the leaderboard of hackathon, a bug bounty platform. So today, like the best bug bounty hunter, according to the leaderboard, is an AI. And therefore, today we say, let's reinvent cybersecurity. We're launching fully autonomous, verifiable agents that protect the blockchain in real time. Unfortunately, that's not the case. Instead, what we actually announce is Web3 projects are getting exploited because they share their seed phrase, because they hire North Korean hackers, and because they install malware as they want to participate on a podcast or Twitter live stream. So now we have an operational security program. We onboarded brands like DYDX, and that works actually well. So let's get the basics right before we jump into the hype. And this is our agenda for today. We do a bit of a reality check, debunk the things that I've just showed you, see how we use LLMs in our daily work. So that means, first of all, we look at the Linux kernel thing and the role of signal to noise. Then we look at the pen tester that climbed the leaderboard. I'll tell you a bit of what I think LLM basics look like and what our perspective is doing research with them, and show you what works with us. So, first point first, the AI discovered a bug in the Linux kernel. So this is a very interesting case because the Linux kernel is one of the, I think, most studied code bases with one of the most, I think, the most brilliant minds on the team as an open source model, as an open source project. And this vulnerability was discovered during benchmarking. That means somebody already had a vulnerability in there, and they wanted to test O3's capability to see how often it would, or how good it would detect that vulnerability in the code base. And then they discovered that there's another vulnerability in there that was not previously detected, but it was the same use after free vulnerability that the thing was benchmarking for. So in the end, O3 really detected a vulnerability that was overlooked by humans and other automated tools. And that means that LLMs are now in fact capable to find complex issues. That's what I would clearly say to that. Now we have to look into the statistics to see how we can use that in practice. So first of all, the source code that was inspected is pre-formatted. So 75% of the code was actually wiped out, and that helped to make the detection much easier. And here are the results. In 8 out of 100 runs, the vulnerability is found. In 66% of the runs, so in 66 runs, no issue is found. And in 28 runs, issues are found, but those are false positives. And then they added another experiment where they did not pre-format the code base. And in that case, only 1 of the 100 runs detects the vulnerability. So what are the key takeaways here? Well, signal-to-noise ratio is obviously poor, and you would need a human to verify all these false positives and not get burned out until they come to these 8 issues that are found. But for me, as a data scientist, the more interesting information in here is, well, formatting the data in the right way can get you an 8x performance boost, and that is incredible. And that's basically a basic principle of data science is, garbage in, garbage out. So it's all about formatting the data in the right way and making sure that the model does not estimate something that is garbage. So, but I want to dive deeper into the false positives. What we see more or less on a daily basis now is that people start vibe coding with an LLM, and maybe with a code base that is large or big, and then they come to us and flag, hey, I found this issue. This is really urgent. I think this project might be exploited by tomorrow. And most people who do that are not security experts, so they have a difficult time verifying these false reports. At the same time, we see circulating AI-generated malicious reports that pretend to have found a vulnerability, and they try to spread basically fear, uncertainty, and doubt in order to manipulate token prices. And the speed is really the problem here. So you can generate a big fake record very quickly, but it takes a long time to verify them. And, well, as we've seen, AI agents are not yet very capable of really verifying it. So there is a time window for financial damage. So who has won in the battle of AI versus humans? Accordingly to a leaderboard, the hackathon leaderboard, it's a AI pen tester. So this is a timeline from February up to now, and currently it's already a bit higher than what's indicated here. So currently this AI pen tester has filed over 1,600 total reports. So first thing that might jump to your attention is, well, that's more reports than this guy on stage has filed since the company was founded 8 years ago. Yeah, that's actually true. And of these reports, 5% are only critical. But then, and also discovered a 0 day. But then, like, these reports are very shallow reports. So a report is basically just flagging a finding. This would be equivalent to flagging an issue. And all findings are again validated before they are submitted by a human in the loop. And 45%, and that says also something, of the findings are still pending due to high volume. So what do we think of this thing? We think that the statistic is a little bit biased, but also we would say, okay, let's acknowledge that we have a tool now that can find standardized vulnerabilities really quickly. And I would make the analogy of this lock-picking gun. So this lock-picking gun is a gun that you can buy in a supermarket. Here you can buy it at Kaufland for 70 euros, so less than $70, a little more than $70. And basically you go to more or less any retail lock and you can open that lock within a couple of seconds. Now, if I run a contests for like a professional lock picker, whether it's this gun, and I give it just a random selection of locks, obviously the lock picker will lose because this thing is just faster. Yeah, the AI on the leaderboard is very different to the AI that we've seen before that was instructed to find one specific vulnerability. That AI is trained to find very common vulnerabilities, and it has difficulties finding complex bugs. So anyways, the takeaway here is that we have a great tool for finding standardized issues. So what are the key takeaways so far? First of all, formatting the code significantly drives performance. And for more complex issues, the signal-to-noise ratio gets prohibitive in that sense that it gets prohibitive to let it work alone. Also, malicious reports are a new attack vector. And overall, AI can improve performance to find standardized issues. So before I tell you how we use AI internally, I want to talk a bit about how I see LLMs and how that informs my thinking. I believe LLMs are basically text generators and they behave non-deterministically. They complete sentences like, this is a zero-day vulnerability, by predicting the next token. So they look at the past and foresee the future, so to say. And the important thing here is, what is the predicted token after this is? Is it this is not, or this is a? And when it comes to predicting that token, it refers to the averages that it has seen in the past. So in general, there are linear and non-linear properties when this text is generated. So the linear property is, what is the next token? And that is the main and dominant paradigm in the whole model, because also our way of writing text is one word to the next, one sentence to the next. But nevertheless, these models are now capable with multi-headed attention and so to digest non-linear complexity. So that there is a map in there that's called the attention map, and that basically tells you if this word is at the relative position 55, you also need to pay attention to the word at the position, let's say, 13. So this map is there to predict relevant indicators. But nevertheless, we always want to basically forecast the next thing. What are AI basics? That is much more difficult, because AI, on one hand, could be way simpler than an LLM, but it could also be a combination of LLMs, so like what we currently refer to as a agentic model. But a basic AI is just a rule set that pretends to be artificial intelligence, so maybe a human or maybe something that is human-like. It could just be a simple if-then rule. So we use a static analyzer. If we find a bug, then we ask the LLM to fix. If the fix is not a fix, how will we find out? Then we use a human to fix the code. And then we use the fuzzer and we continue to do the same thing. Right. That also means that we've now just gotten one additional tool to build an AI that can help us to find bugs. But you see that it's like writing code. Yeah? The complexity is infinite. And the big question is the engineering question, how to get that right. And we believe that there's currently no tool available, and we're doing our own research that can on a production scale, industrial scale level, outperform humans significantly. We've done some research, but here are some takeaways that I want to give you if you want to try out to tune hyperparameters or just to play with the LLMs. My suggestion is to let the LLMs do the tedious, not the complex work. That means also enhancing the data can be done with an LLM, but you have to enhance the data yourself as well and format it to be as linear as possible. Like the best case would be that you just use one happy path and no recursion. Obviously, some programming languages require a lot of recursion. So what you do here is, what I've had success with actually was that you just put the function call in there multiple times. So it sounds really stupid, but we've seen performance increases of that, and it is stupid, but it makes so far use of a logic that the LLM itself has a problem with back referencing and recursions. The maybe more realistic case, if you don't want to look at only one happy path, because then you are likely not going to find any bugs, is you remove the boilerplate and maybe modules with minor security relevance. Very, very important, whenever you work with a LLM, is be context conscious. So you need to use some context to clarify your goals and set up an agent that can work in a certain way, but avoid multi-shot prompts at all costs. This adds nonlinearity, and it makes the agent think that this is kind of a discussion, and it generally, if you don't work with a foundation model, the agent, or most LLMs, will generate rather an engaging discussion if there's one question from you, one reply from them, and then you ask something again. That looks like a conversation, and this gets you easily in the state where the conversation, just by the average thing that it looked at before, will continue for a while. And so empty context is better also because model performance decreases with larger context. Obviously, a bit of a no-brainer is use specialized agents with system prompts, for example, a separate agent to generate POCs. And don't get lost in hyperparameters and fine-tuning unless you have really relevant stuff to look at those things. Especially, I think we played around with fine-tuning for almost a year with one to two people, and the foundation models just evolve so fast that getting good results with fine-tuning is really cumbersome. Same is true for hyperparameter tuning. So now I tell you, use empty context or make it as short as possible, format it, right? The question is always what does that mean? What does that mean exactly? And to evaluate that, or answer this question scientifically, you would need a research pipeline to basically make database decision on that. And then that gets very difficult because you need multiple outputs at the same time for different context lengths, and you need a lot of sampling to get it right. So how do we use LLMs at Oak Security? We integrate them very well in all our audit workflows, but we do not replace any kind of real manual work there. We use it mainly for code summarization and for onboarding, finding common vulnerability patterns, like the no-brainers make it easy to flag things, generating drafts for our internal documentation, but also for eliminating spelling errors in reports, for example, and drafting issues in a concise manner. Also, LLMs can be great for triaging. There, I would even say that cluster analysis or like conventional ML things can work even better. That can be also upscaled for larger systems. And in the end, like all output that LLM generates is validated by auditors. Even with AI, the audits might miss vulnerabilities, so there is no guarantee that an audit or an AI audit might find the issues that are in your code base. So we advocate strongly for this Swiss cheese model, where you have multiple layers with cheese with holes in them. And eventually, through one slice of cheese, something might slip through. But if you layer a lot of cheese on top of each other, then hopefully you're not going to see the bread below it. And yeah, same is true for issues. You can do way more than just audits. So in the specification stage, you can write great documentation, simplify the architecture, map out and plan your operations. This is also where you can consult us and ask us, hey, what can we do better when we onboard interns? You can already think of threat models and how things can go wrong. During development, you can develop in-house best practices for code quality, readability, and so on. Do internal reviews where you just share your code with a colleague, ask them to comment on it. And I'm not going to go through all the list, but the main message here is if you go from the specification to a post-deployment stage, the post-deployment stage is more expensive. Obviously, you can do bug bounties there or monitoring and alerting, but this tends to be very expensive, especially when a disaster already happened. Another thing is, it's actually not the code that gets broken in Web3. It, like most of the time, like the most severe issues are operational security issues, and I really want to drive that point home today. Here, Bybit and Ronin Network, they're both cases where secrets got leaked. So in the Ronin case, it was really, I think, seed phrases and keys, and in the Bybit case, it was a session token on a developer machine that changed the front end of Safe. If you want to find out more, let's connect, and I'm happy to talk about this. Also, if you have any questions, give me questions. Thanks.
So if there are any questions, please raise your hand and I'll bring you the microphone. Any hands? If there are no questions, do we do comments? Yes, one, well done. I'll bring you the microphone.
Hi, thanks for your talk. I'm interested in what you think specifically about AI and LLMs being able to review smart contract security. Talking specifically about smart contracts, do you think that eventually we come to a point where LLMs can become better at humans at detecting vulnerabilities in smart contracts? Since I think for the most part it's about not some bug that exists, but something that we've overlooked, and LLMs can over time become better and better at detecting these issues that humans may have overlooked on smart contracts specifically.
So my thought here would be that it's basically the same thing as, I mean, we use that for smart contracts, and we have the same problem, like the signal to noise ratio is the main problem, that they, in theory, can detect things, but then they detect so much false stuff that you need another human to verify all the LLM outputs, and then it's the question, should the human look at all the false outputs, or should they spend the time at the code? And I, like, my basic intuition of building AI is that it's not an LLM that's going to solve this issue, but it's an AI, and the AI will be a combination of automated tools which include fuzzers, static analyzers, agents that write a POC, and maybe also an LLM that looks at the code. But it could even be a kind of compiler that compiles the language to a formal model and then automizes formal verification. So the problem here is that it's also a giant set of possibilities that you have, how you combine those tools. And it's the same for any programming languages. I think for smart contracts, there's another problem, like smart contracts are a newer thing, so there's less data on smart contracts in large language models. So for newer smart contract languages, there might be nothing in it. And then the vulnerabilities that are in smart contracts are also not the standard vulnerabilities. So I've seen LLMs flagging a use after free vulnerability in a Solidity smart contract to me. So they find the vulnerabilities that are common vulnerabilities. They don't find necessarily the vulnerabilities that are in the code base, right? And that is really the issue with LLMs at this point in time. Obviously, at some day, I hope our cars will fly, and I hope that the LLM is going to do our work. I like that vision a lot. And yeah, if you want to help me build an LLM that can replace me, I would be very happy to do so, but I've failed so far. Hosts. Any other questions? There's one.
Yeah. What is it?
Behind you.
Yeah.
I mean, isn't it that LLMs will be used by the attackers as well, and also the security teams? So whatever vulnerabilities that you find through LLM will be basically zeroed out. Like, I don't think, any new attacks could be happening from the vulnerabilities that are not found by LLMs. And also, I feel that LLMs may not really play a significant role because both the attacker and the security people have access to it, right?
Yeah, I think that is a very important point. I think it's first of all, it's that writing exploits is also much easier, and it's easier to test and verify that the exploit works than maybe triaging false positives. And but there's another thing with LLMs. With LLMs, people start vibe coding. So what I would call the unit test quality of the code is, I would say, has improved or has become better than maybe it was 3 to 4 years ago. But the integration test quality of the code has really deprecated with people vibe coding. So I think there's a second factor, that people build code with LLMs, and this code is on average more complex and has more complex vulnerabilities in them because it's just built quicker. And usually you would decide to either you build something complex or either you build something easy and fast. And with LLMs, I think people start doing both at the same time, and this is a risk. Hey.
Last one.
Yeah, I'm also concerned about the use of LLMs there for writing all these tests. What would you, in what you've seen, like that unit test quality improved, but integration test quality went down? What would you say is the reason? Is it because the integration tests require an actual understanding of the overall infrastructure?
Yes, exactly. So LLMs are very good at doing things in a small context window. And as the context window expands, the even like multi-headed attention cannot pay attention to everything. And if you build something that isn't there yet within the code base, that is an outlier for an LLM. So it's basically an error, and getting the LLM to produce basically an error as we would see it is a new feature. So for us, this would be a new feature, but from the LLM's perspective, it would be an outlier, something that is not in the dataset. And therefore, the complexity is the main thing for the integration test.